Hello and welcome to today's webinar, Kistler Sensors for Transfer Path Analysis in Automotive Application. Thank you very much for taking the time to join us today. My name is Markus Meissauer and I'm a sales representative in the business unit Vehicle Testing for Germany, Austria and Switzerland. So I'm your consultant for NVH applications. At first, I will inform you about some technical points. We would like to inform you that all participants are muted. The webinar will be recorded and recording will be shared with you afterwards. Please feel free to drop questions in the Q&A section at the topic. We will answer all questions by email after the webinar. I also welcome our speaker today, Mr. Roberto D'Amico. Roberto is business driver for NVH in the vehicle testing business unit at Kistler. He holds a PhD degree in noise and vibration from KU Leuven in Belgium and has around 15-year experience in NVH with focus on automotive. Within automotive transfer path analysis is being used more and more to address several NVH aspects, from troubleshooting to development, to prototyping and predictive analysis. In general, transfer path analysis requires measurement tools. The choice and accuracy is key of accurate and successful transfer path analysis. Kistler offers several sensors which can be used for transfer path analysis in automotive, and it's the goal of this webinar to provide an overview together with a review of their strengths to support at best transfer path analysis measurements. The webinar will start with a short introduction to transfer path analysis for automotive, and next we'll review Kistler acceleration, force and wheel force measurement sensors for transfer path analysis. At this point, I will hand over to Roberto, who will guide us through this interesting subject.
Hello, everybody. Good morning, good afternoon, or good evening, depending where you're sitting today. Thank you, Markus, for the introduction. So let's jump into the first section of this webinar that we have today. The goal here is to just set a little bit the scene, give you a short introduction to TPA. Those of you who are experts in this field might want to excuse me for the very short and crash course that I'm going to give in transfer path analysis. It is just serving the purpose of giving an overview of what are the types of transfer path analysis we have around and what type of measurements we need to carry out. So let's start into that with a short intro. And let's start with the link that we have between sources, paths, and receivers. So this is basically the starting point for transfer path analysis. And this is a concept that is familiar to most of you who work in NVH. When it comes to automotive NVH, of course, we always have a source, which could be the engine, nowadays more and more motors, wheels, gearboxes, and so on and so forth. These sources excite the structure, and the excitation is transferred to the receiver. And the transfer is taking place through a transfer function. And it is received in the form of vibration or sound pressure, for example, and so on. Now, it is important for transfer path analysis to decompose the problem in this way, because that's exactly what we want to look at closer. So we want to look closer at the source, at the transfer, and at the receiver. And it is important also to understand each of them better in certain situations. Because if, for example, we have a source which is exciting at a certain frequency, a resonance frequency of the transfer, so of the path, then what you might end up into is a condition that probably is exceeding your targets, because maybe you have some targets that are established in a way that are aligned with some vehicle level performance. You might want to know if the source is not exciting a resonance frequency, which might be a dominant resonance frequency, but because you're not exciting it, probably it does not give you any issue. So all in all, what I want to tell you is that transfer path analysis is going in this direction. It's going in the direction of separating the source, the transfer, to understand better what is happening at the receiver, and then to try to design, model, and engineer the type of behavior your system is going to have. Now, when it comes to the role of transfer path analysis in automotive engineering, as Markus correctly stated, this approach is increasing in relevance because it allows to address common challenges in automotive NVH. For example, we can understand which sources are contributing most to a certain receiver, which are the main transmission paths that the noise and the vibration are taking, how do sources and paths interact, as I just mentioned in a previous slide, or for example, more advanced issue like what is structure-borne and an airborne issue that is giving us problem, because of course you as engineers want to take a measure against that. And of course, structure-borne and airborne issues have different measures to be taken. These are just a few questions, but of course you name them. I mean, there are many of them. I'm pretty sure you have many more than this. And the reason why transfer path is becoming increasingly common is because it can address a wide range of application areas. For example, in the vehicle development, troubleshooting, prototyping, validation, target setting, but also more and more predictive analysis. Because of course there are, we will see it in a minute, there are some TPA formulations which exactly allow you to do that. So to predict how your system will behave under certain source and path conditions. So having said that, let's jump into really let's set the scene. Yeah, let's set the scene and let's introduce the key players of TPA. So when it comes to TPA problem, like in this case, we have a simple car with an engine. What could be an engine, for example? You will have an active source, which in this case is the engine. We make an assumption that you can't measure the exact source, so the influence which is making the object vibrating. Of course, we know that in many cases this is possible. Like at Kistler, we know well that you can measure the pressure in the combustion chamber. We do have a rather broad product line of in-cylinder pressure sensors for that. But we assume that we can't measure that. We are not interested in that. We only know that the active source is vibrating and is transmitting the vibration to a receiver which is passive. So we assume that it is not vibrating, it is not exerting influences, let's say. It's just passive. And this is basically the structure of our car that we have here in the picture. And the two communicate with each other through an interface point. So the interface point is the point where the forces and the moments are transmitted from the source to the receiver. If you want to refer to more mathematical formulations, and I promise you, I'm not going to go today into mathematical details of transfer path analysis, we have a rather intuitive relations for those who are expert in these fields. And this is that basically the response at the receiver can be calculated as a sum of contribution from the sources. And this transfer is happening through, for example, the admittances. So the admittances, of course, of the structure with the receiver plus the source. Of course, this formula can take many different forms. I agree with you, it's a little bit simplistic, but it gives a good idea of the entry point for TPA. And now when it comes to TPA, I want to mention that from a measurement perspective, because we are going to go in that direction, we have two levels of measurements. We have operational measurements and FRF measurements. We also have a third level. We need to go to the analysis. We need to analyze the data and we need to extract the information we're interested in. So either loads, paths, or maybe we want to do some predictive analysis. But it is important that this phase is also needed to extract information for what you've measured. Over the last decades, I would say there have been very many declensions of TPA developed. I find this classification pretty nice, and this is taken from the paper that you find the reference at the bottom of the slide. And this is done in classical TPA, component-based TPA, and transmissibility TPA, transmissibility-based TPA, which we are going to review in a minute. Each of these methods includes a variety choice of possibilities when it comes to the measurement and the assessment of certain quantities. And in this paper that I indicated to you, you will find a nice review of most of these. Let's jump into classical TPA. Now, as I mentioned, we have a testing phase and an analysis phase. The testing phase usually has two subphases. We have operational measurement and FRF measurements. In the operational measurement, we go back to our model with a vibrating engine and the body in white of our car. What we want to measure in this phase is the interface force between the vibrating engine and the receiver. So basically, we want to measure what is happening right at the interface in terms of exchanged force, of interface forces. Of course, the forces that you're going to measure are dependent both on the source and on the receiver. And what you're going to use from a measurement perspective here are generally accelerometers and force sensors. Of course, to measure here, you have generally three methods. This is direct force measurement, mount stiffness method, or matrix inverse method, which are different methods which allow you to calculate the interface force. Once you've done this, you're going to dismount the engine and measure the FRF on the receiver only. And this is a very common measurement, FRF measurement, which will involve the use of course, accelerometers, probably microphones, in some cases force sensors, and of course the excitation. So impact hammers, you're going to have the shaker, for example, with an impedance head or acoustic sources. But here you're basically carrying out the measurement on the receiver only. Then we have the analysis phase. In the analysis phase, what you're actually doing is applying the load to the transfer function that you have measured. And this is done on the receiver only. With such a formula, you can actually calculate the response on the receiver. And this will be only related to the couple of source and receiver that you have at hand. And now this is an important statement because it means that if you're changing the source, you're going to have to do the measurements again. If you're going to change the receiver, you have to go to do the measurements again. And this created sort of limitation, of course, because if you wanted to use this approach for predictive analysis with multiple sources, for example, you were a little bit bounded. Therefore, what researchers and engineers have been doing was developing an approach which is called component-based TPA, which we will now quickly review. And this approach, I must tell you, is basically nowadays the most widely used. So if you look into the literature, you're going to find a wealth of papers, information, researchers, engineers who apply these methods to predict and do much more with it. What is the difference with respect to classical TPA? So again, you have a test phase, you have an analysis phase, you again have operational measurements, but this time operational measurements are done in a way that they allow you to calculate interface forces, but they must be invariant from the receiver. So usually it is very common to put at one end of the source a very rigid block. This is why it's called blocked force measurement. And this block theoretically should allow you to estimate the forces, the interface forces, independently from the receiver. So only you will obtain an information which is only related to the source. There are other approaches to estimate an interface force which is independent on the receiver, which is, for example, the in situ estimation, which is also growing in relevance, I would say. And then you have a free velocity approach, which is less used with respect to the other two. I would say definitely nowadays blocked force is on the hype. We see a lot of applications for blocked force, and this, I think, it is so the fact that you're actually isolating the forces from the receiver, this is pretty interesting. So adding invariant forces is the strength of component-based TPA. The main measurement tools here are usually accelerometers and force sensors. So you want to measure these two quantities. And then once you've done that, you move to FRF measurement. FRF measurement is pretty similar to what we have seen before. What you do according to the formulation you're using, you could measure the source and the receiver together and measure the FRF. Of course, you will see in the minutes that it could be also a little bit different from that. But here, as I mentioned before, the tools you're going to use are the same that you have used, like I explained in the previous slide. Then you go to the analysis part, and here you can again predict the response starting from the invariant interface forces, so for example, blocked forces, and apply them to the FRF that you have measured in the second step, so in the FRF measurement. But if you apply some mathematics, some clever mathematics to the formulation, you can actually be able to decouple the source and the receiver. Of course, as you see here in the formulation, I'm not going to go into the details, but basically you will have to evaluate the transfer function between on the receiver alone and on the source alone. And this will allow you basically to get to a very powerful conclusion because you're going to be able to exchange, for example, various sources. This has tremendous impact on even the way suppliers and OEMs can communicate. If you think about that, an OEM would like to test multiple motors can now share this information with a supplier, can get this information and can try to do predictive analysis. So this is why component-based TPA is gaining ground more and more. And this is why I think in the future we will see this more and more, with the blocked force being predominant and the in situ measurement also being a very, very interesting approach to measure force interface invariant forces. We have a third class of approaches. These are called transmissibility-based TPA approaches. Here I mentioned mainly the operational TPA, so OTPA. There are also other approaches like OPACs, for example. And when it comes to operational transfer path analysis, what we are doing is sacrificing a little bit of information that we have at the end of the analysis and gaining time, basically. What we do in this approach is not any longer to measure interface information. We take the measurement usually on the receiver. We try to measure what is happening, for example, around the source, or we try to measure what is happening in terms of transmission paths. We let the source run under different conditions to get a good statistics of our transmission information. So for example, if it's an engine, we let it run at multiple RPMs, for example, to get a more refined information regarding the transfer functions. And then what we get at the end is a refined information regarding the contribution paths. Of course, you are able to do this in a much faster way than what you had with the classical TPA or component-based TPA, but of course you sacrifice information. Let's now draw some conclusions and let's try to make a little bit of sum up of what we said so far. I know I've been going through a lot of information pretty quickly. This is usually taking hours, if not days, to explain, and I'm trying to squeeze it into a few slides. Let's have a look together, though, at the table here. We have three classes of methods. We have classic TPA, which relies on operational measurements and what you're going to get out of it is interface forces. And of course, you will perform also FRF measurements on the receiver, and you will be able to obtain as an output loads, more information about the loads, more information about the contribution paths in a rather simple fashion, but only for a specific receiver source couple. The component-based TPA allows you basically to characterize the source independently from the receiver, which is a huge advantage. From an operational measurement perspective, you have to measure the interface forces invariant of the receiver, basically, and the FRF measurements. This has to be performed as well. At this point, you're able to do not only load identification and contribution path analysis, you will also be able to do performance prediction with the information that you've got. Third, we have transmissibility-based TPA, which tries to estimate the transmissibility information from a certain location to the receiver. Of course, it is extremely quick because you don't have to disassemble your vehicle, for example, or your assembly. And it's, of course, limited, gives you information limited to the contribution path. But now let's have a look at the type of measurements that you have in TPA. So you can have, of course, many different applications. Like you see here on the right-hand side, I mentioned just a few, like engines, motors, steering columns, pumps, and auxiliary drives, as well as tire and suspensions. I mean, even if you have a look at the literature, all these cases are rather common. And of course, there is a reason for that. Yeah, it is because these components generate an excitation to the vehicle, and most of the engineers want to understand better how they excite the structure and how this excitation gets transmitted to the receiver, so to the passenger. Generally, you measure acceleration, forces, and moments. Like for example, in the case of the blocked force, we said it's very important. And of course, acoustic pressure, which it is not going to be the topic of today, because Kistler mainly focuses on structural quantities. And of course, when planning your TPA test, there are a few things that I would suggest you to keep in mind. So first of all, I would suggest you, when you're planning the test, to keep in mind the goal of the analysis. These will drive the choice at methodological level. So what type of method you want to implement. Second point is that you need always to keep in mind that the measurement accuracy is extremely important. So in TPA, because of its mathematical formulation, errors might easily accumulate. So if you don't have accurate data in your hands, it might be that these will lead then to pure prediction at the end, or poor information. So keep that always in mind, that accuracy is important when you're choosing the tools with which you want to measure. There are many cases in which consistency and repeatability is important. As I mentioned, component-based TPA gives you the chance to change, for example, the source, testing different type of sources. Therefore, you want to maintain a certain consistency and repeatability in the way you measure. It is very important to maintain a certain integrity in the accuracy of the test outcome. And finally, the last point is that when you're considering multiple measurement technologies, keep always in mind the pros and the cons you might want to have. So all the advantages and disadvantages you might have with such a technology. Now we move to the next slide, where I want to focus a little bit on a topic which I think is very relevant when it comes to measurement. Now we talked a lot about interface forces, but interface forces can be estimated or quantified into different ways, as I mentioned before. Either you do that with a force sensor, so just placing a force sensor in between the active source and the receiver, or you could also consider doing the so-called in situ measurement, or exploiting anyhow the fact that acceleration and forces are linked through some sort of transfer functions. So indirect force estimation, I call it. In the first case, of course, what you do is measuring the force. So the measurement is actually force. In the second case, you have acceleration. So the measurements are different. I want to have a look with you at some pros and cons of each of the two methodologies, because I think it is very important to do this. In terms of pros, of course, when you have a force measured with a force sensor, you have that the measurement is force, and also the moment can be back estimated by the force itself. So it is, when you want to measure force, here you're just when you want to quantify force, you're just measuring force, and this is a good thing. So you're going to get rather high accuracy also for force measurement. And in general, when you're using force sensors, you rely on a very good consistency and repeatability, because they are actually built in a way that you are not probably going to change the setup very often. Therefore, if you want to measure multiple motors, you can just keep the setup like that and move on. In terms of cons, we have the fact that integrating a force sensor into a test object might require engineering effort. Well, in most of the cases, it is like that. And of course, you have to account for that. Also, the available packaging space around the object might not allow to host a force sensor. In some cases, the available spaces in automotive are extremely narrow, and it's not easy to fit a force sensor. The third point is about the accuracy. When you measure blocked force, for example, you always have to take into account that your block is not going to be perfectly rigid. So it's still an elastic piece of steel probably. Therefore, it might contribute to the response. And it is important that when you decide to measure with force sensors, you keep that in mind and try to make sure that the dynamic behavior of the test rig or of the block is under control and you master it. On the other side, when it comes to acceleration sensors, in terms of pros, of course, they are easy to mount, position, and move around. So you don't have to modify the testing object. They are easy to use. They are small enough to fit nearly any environment, so you don't have problems of space limitations and so on. And finally, a third good point is that under certain conditions, like for example, when it comes to in situ measurement, they could be actually more accurate for higher frequencies than the force measurement. And this is shown also in the literature. So these are the pros, while on the other side, we also have some cons of estimating the force with accelerometers. So first of all, the primary measurement is actually not force, or it is not moments, it is acceleration, and force is calculated indirectly, so you have to take that into account. The accuracy of the force estimation is, of course, sensitive to the amount of accelerometers that you're using, their position and orientation. So you have to take that in mind, keep that in mind, and you have to keep in mind the fact that in general, for low frequencies, you should expect a low accuracy with acceleration measurements, so with estimation from accelerations. Of course, this is case dependent. It's not a general rule, but what we see also in the literature is that. Of course, measuring with accelerometers requires additional transfer function measurements. This has to be considered. Estimating the moments with accuracy might be challenging, and of course, case dependent. Also, here is not a general rule, but you have to take it to consider how you're going to measure those moments. You have to consider that you might want to have some sort of consistency and repeatability when you're measuring with accelerometers. For example, if you have measured blocked force with your accelerometers and then the setup is dismantled, then once you're mounting that again, you might expect a certain inconsistency between the data because of that. Keep it in mind. Keep in mind this consideration when you're testing. And then finally, a precise knowledge of your sensor position and orientation on the geometry might be required to get an accurate outcome of this calculation. So you need to know where the sensor is positioned. And with this, I just wanted to give you an overview of the type of points to consider when you're measuring, when you're estimating or quantifying forces, for example, for blocked force or transfer path analysis more in general. And having said that, I move to the next section, which starts exploring our product line. And by the way, just one last thing. I think here again, I mentioned the source that I told to you about. If you want to know more about the theoretical basis, just have a look at it because it's really comprehensive. And now let's talk about acceleration sensors from Kistler. Let's have a look here in general at the advantages of using accelerometers. Acceleration is, of course, the most used quantity in TPA, and this is clear. The measurement is very important for vibration. Of course, we want to measure at higher frequencies, so that measuring acceleration is pretty the natural choice, I would say. It is easy to mount and position an accelerometer. This is why they are used a lot as well. And they are small. When the geometry gets complicated, they are easy to position. And how to select a sensor for transfer path analysis? Well, here we're mainly talking about IEP sensors, so sensors with integrated electronics and triaxial sensor to maximize the information you can get from it. Typically, the ranges go between 5 and 500 Gs. Here you find a table which can kind of guide you through the choice depending on your application for TPA. So this has been done just for TPA applications. Of course, if you're measuring an FRF, you might want to go lower in G range. If you're measuring on an engine, you might need to go higher in G range. This is clear. What is important for TPA might be the mounting possibilities. So the mounting must be easy in general, and you want to have flexibility in orientating the sensor. This is because, well, as I told you before, the way you position the sensor might be impacting your analysis as well. So keep that in mind. You might want to have TEDs, Generally, TPA, you don't do that with 2 sensors, you do that with more sensors. Therefore, having a possibility to import all sensitivity just with one click of your mouse might be a good thing. So that's a good option. If you're planning to have hot applications, having a good thermal performance is also very important. We will see this in a couple of minutes. And then finally, pick the frequency range, which is aligned with your goals. Of course, if you're analyzing the full vehicle, then probably you're not going to reach 10,000 hertz. But if you are analyzing sub-assembly, you might want to have a wider frequency range. So keep that into account so that the sensor is delivering you the best accuracy. And if you want to know more about selection of accelerometers more in general, please have a look at our on-demand webinar on the on our webpage. So you can just go there. The name is Selecting the Right Accelerometer for Automotive Applications, and you will see how to select the accelerometers. Let's now have a look at some products. In general, for TPA, the most used sensors are these 3 here. So we have the 8763, which is a sensor available in a variety of G ranges and reaches up to 15,000 hertz in terms of frequency range. So it goes pretty high frequency. Nowadays, we have improved electronics and we can reach up to 58 lower noise levels than what we had before. So it's a pretty good improvement, which allows, so in case you're doing TPA, allows you also to use these sensors for FRF measurements on vehicle level, and also measurements on e-motors and so on. This sensor mounts has 3 threaded holes, one on each side, like you see here in the picture. And this is a very nice feature for TPA applications. Why? Because you have the possibility to orientate the sensor and the cable in the direction you want, like you see here. So this is a pretty good feature. And for us, it allows you to deliver to you a very accurate calibration. So we can screw the sensor onto the shaker and calibrate on each axis. So the calibration information is pretty accurate. And then it has a wealth of mounting possibilities. So you have various possibilities, and you can use this sensor attached to the structure the way you want, basically. Then we have an 8764B. There is a sensor also available in a variety of G ranges, also with a wide frequency range. And this sensor has a nice characteristic that it has a true hole. It has a true hole, and with this you can orientate very easily the cable. So you can move the cable 360 degrees, and you can screw the sensor to the surface if you wish. So maximizing the connection stiffness, basically. This sensor also has an integral isolating pad, which makes it immune to ground loops. Very nice feature actually for measurements on electric motors, for example. And it has a very narrow, low profile, so it's good for small spaces. Finally, we have an 8762, which shares with the 8763 the 3 holes, one on each side. It is a little bit larger sensor, so I would use it for example, body-wide testing, FRF measurements, where you might want to have lower G ranges, because actually the sensor goes down to 5 Gs and 10 Gs, which is pretty good for those type of applications where you have an excitation which is not reaching very well, for example, the response. Of course, we do have a variety of additional accessories as well, like impulse hammers, impedance head, cables, IEP force sensors, and so on, which can be used for TPA as well. Then I wanted to talk to you also about applications in hot areas. And here, what Kistler has to offer is the piezo star crystal. Now, piezo star crystal is a proprietary technology of Kistler. We do produce this crystal only in our production laboratories, and it differs from industry standard sensing elements like ceramic or quartz for certain characteristics, which also make piezo star suitable for high temperatures. For example, with respect to general, typical ceramic performance, the piezo star has a wider temperature range, so it can be used at up to higher temperatures. And while the ceramic element, like you see here in the picture, it drifts a lot in terms of temperature sensitivity. So if you change the temperature, the sensitivity of the sensor and the data it delivers are deviating, and it's difficult to control that, the piezo star provides you a nearly flat performance over the full temperature range. This is actually topping the market in terms of thermal stability. And it's even better actually than quartz. Very often quartz is preferred to ceramic because its thermal properties, but actually piezo star outperform also the quartz. And with respect to the quartz, it can be miniaturized. This allows the piezo star to deliver sensors which are as small as ceramic sensors, but with way better thermal performance. And this crystal is implemented. Here you can see actually what happens in terms of performance. So if you have vibrating surface measured with piezo star and ceramic at the same time, and you warm it up, you see that afterwards there is a difference between the piezo star and the ceramic sensor, and this is due to the thermal, so to the temperature change. So whenever you have to deal with engines or hot areas and you want to measure, this is the piezo star is really the choice. And we have two sensors here. We have 8766, which looks pretty similar to the 8763 you have seen in the previous slide. And actually it is, because it still has the 3 holes on each side for easy mounting. It is a light, small sensor. It is ½ inch, so it's about 10 millimeters. It's rugged, available in a variety of G ranges. But of course, it mounts piezo star rather than a ceramic element. Therefore, it delivers an excellent thermal performance with TEDs. We have a version with TEDs up to 165 degrees, which makes it really an extremely good sensor. We have a version also with through hole and integral isolating pad, which make it easier to orientate the cable and protect the measurement from the ground loops. So it's ground isolated. So with this, I conclude the overview of the sensors of the accelerometers that Kistler can offer for transfer path analysis application. And I then move to the second section about products regarding force measurement. Let me give you another crash course in piezoelectric technology for those of you that are not familiar with that. Basically, piezoelectric technology is based on the exploitation of the piezoelectric principle. There we have, whenever you have actually piezoelectric material, which is put under load, under a mechanical load, the material is going to produce an electrical charge. The electrical charge is then taken out of the sensor and transformed into a voltage signal with a charge amplifier. This is very often happening outside of the sensor, but it could also happen in some cases inside the sensor. Depending on the way you cut your piezoelectric material and on the type of measurement you want to carry out, you can combine multiple layers of crystals, for example, or piezoelectric material layers, in a way that it will provide you with a charge which is proportional to the load in a certain direction, for example. Therefore, with this idea, you can combine and obtain forces. You can combine piezoelectric layers and obtain forces in multiple directions, for example, and get a force sensor. And you can combine force sensors and get a dynamometer, which measures not only forces, but also moment in multiple directions. So you can get up to 6 components overall. And of course, I need also to make a comparison with a technology which is also widely known, like strain gauge, the strain gauge technology, which is based on extensimetry. So basically, when it comes to piezoelectric measurement, this is very interesting for vibration application, for dynamic applications, because generally the structure is pretty stiff. And being pretty stiff, you can actually reach higher frequencies. When it comes to extensimetry, the whole concept is based on the opposite idea. So elasticity, the object on which you're putting an extensimeter strain gauge, actually has to deform to give you the output that you desire. Therefore, the first difference between the two is the application area. Another thing is that piezoelectric measurement allows you to get a wider measuring range. And I find also very interesting to show this example here. So this is the Rodin P530. We will see this in a couple of slides. And this sensor has a 30 kilonewton measuring range. Now, if we place a 50 gram, a small part of that weighs 50 grams on top of it, you can see from the measurements that the tool is able to measure that. And this shows you that with piezoelectric sensors, you really have a wide measuring range. And this measuring range, as well as the signal to noise ratio, can be adjusted outside. I mentioned earlier that you have a charge amplifier that is gathering the charge and is also doing the signal conditioning. Another nice thing is that you can measure very small forces, very small force changes with high static preloading. For example, this could be interesting when you have an engine, you have it on the engine bench, and you're basically already loading with a static load the piezoelectric force sensor, and then the engine vibrates. You can still measure very accurately the forces, the dynamic forces. You also have high repeatability. You have possibility to have overload capability because it's very stiff, and you have rather long calibration intervals. On the other side, when it comes to ostensimetry, it is easier to install a strain gauge, so it's easy to glue it on a surface. You don't need to introduce preload, which you do for piezoelectric sensors, and it is easier to handle the cables, which in the case of piezoelectric sensors must be so it's an issue you must take care of so that they are not too long for the application you have. So this is a little bit an overview of the differences between these two technologies. And when it comes to TPA applications, there are a couple of points I just want to mention. So first of all, of course, piezoelectric technology is more suitable for TPA because it's stiffer, so it allows you to get higher in frequency in general. Of course, this does not mean that strain gauge is not to be used, but definitely I would rely better on the piezoelectric sensor if I could. In terms of choice, I think that you must always keep in mind that the load range has to be identified well in order to identify the piezoelectric sensor that you need. And also you have always to keep in mind the packaging space because that's a key requirement, so a key constraint more regarding the application you're going to have at the end. And at this point, I just want to give you an overview of the product line that Kistler has for piezoelectric force sensors. I must honestly tell you that the piezoelectric force sensors at Kistler, so they belong to a very wide portfolio. And what I did here was just trying to identify for you the most interesting products for TPA applications. So we have single component force sensors that measure the vertical load, available in a variety of measuring ranges, and some of them go up to 200 degrees C, so for hot areas. Of course, these are highly stiff components, so they allow you to cover rather broad frequency range and with very low noise threshold. If you have less space, we do have the slimline single component force sensors, which allow you to measure not only the vertical component, but also the shear. And also here we have a variety of measuring range, but what is astonishing is the dimension. So here you have the 8763 that you have seen before. This is about 11 millimeters. This is 8. So it's extremely small, can be embedded into a very small packaging space. And then we have 3 component force sensors that measure in the 3 axis, in 3 direction the forces. Again, a wide variety of measuring ranges, and again, a very high stiffness to cover a broad frequency range. However, these sensors will be embedded into a frame, into a housing, which then must be preloaded and calibrated in some cases. Otherwise, we have products which are ready to use, which are called force links and dynamometers. Basically, here the components have been already embedded into a standard housing, and they have been already calibrated, and they are already calibrated with the housing and already been preloaded. We have three component force link, for example. We have 6 components force sensors, also very used actually these in transfer path analysis, because they can give you not only the forces in the 3 directions, also the moments. And we have the dynamometers, which also allow you to measure multiple components. And at this point, I show you a couple of examples of applications. For example, for blocked forces, it is very common to have a specimen which could be a motor or a gearbox which is connected then to the mounting, and then you have the dynamometer connected in between the mounting and the block to measure blocked force and blocked moments, of course. Probably you want to optimize the damper, or maybe you want to quantify the performance of the specimen. So they might have very diverse applications, but they always allow you basically to measure the interface forces like we have seen during the introduction. So these are key quantities for TPA, and with these sensors you can directly measure them. Otherwise, you can have a specimen which could be an auxiliary drive, a small motor that gets connected to a block. And in between the specimen and the block, you can have a force link, which is basically ready to be mounted. You see here in this picture. And thanks to that, you can measure the blocked force between the specimen and the block when the small bench is basically regulating the performance of the specimen. So you would have a torque sensor, brake, and so on. And by the way, Kistler also has products in this direction. If you're interested in motor testing, please have a look at our website and get in touch with us to learn more about it. Of course, we know well, and I guess you know well, that off-the-shelf sensors in many cases might not be enough, especially when it comes to automotive, especially when it comes to TPA. The packaging space that you have available is pretty complex in terms of shape. The loading conditions are unique. You might have a special motor or engine which has a performance which is not able to be fulfilled with a standard sensor, and therefore you want a sort of unique solution. Maybe the environment is a little bit application specific. You have certain influences, maybe it's particularly aggressive, and therefore, as they are unique applications, they require a unique solution. This is why what we offer at Kistler is also customized solutions to address them. Basically, what we offer is a possibility to even replace the original geometry with a certain geometry and measure up to 3 forces and 3 moments, so depending on the application. Of course, everything is fully tailored to the application and the requirements from our customers. So actually, we do discuss together at the very beginning of these projects what the performance should be. And the nice thing is that we can offer our customers more than 60 years of sensor technology know-how and engineering. So these the force products Kistler has been doing for more than 60 years, and we can provide all of them to our customers when they come to us under a turnkey solution, because we start with the design production, we go through calibration, which by the way is a very important operation because this is really a part where we put a lot of our know-how to make sure that after we have designed a sensor, we are able to tell our customers what type of output this sensor will have under certain loading condition. And of course, commissioning and servicing are part of what we offer to our customers. And we realize these are very important. We have several projects on TPA, and therefore we have decided to establish a team. So you're going to have a dedicated Kistler team, which is called Custom Product Lane. And the goal of the Custom Product Lane is to execute this type of design and project in order to be really customer dedicated and customer specific, following the original requirements. Some applications of these customized force projects are here, where we do mainly blocked force measurements. So you see here some sensors for measurement of the blocked force from an auxiliary drive under various conditions. So these are two different sensors actually. Of course, they go through a CAE optimization. So you will have finite elements optimization so that the performance is predicted in advance, so that it responds to the original requirements. And also, of course, the CAE is consisting of the CAD optimization, so that the final shape is actually within the boundaries that the customers are requiring. One of the points where we put a lot of attention is making sure that the natural frequencies are as high as possible, and this is very important for TPA as well as the calibration process, which is definitely state of the art. Like you see here, we have our machine for 6-component axis calibration, which is really advanced and allows really high accuracy and traceability. Now we jump into the final section regarding the sensors for TPA, and these are wheel force products. So what we see is that mobility is developing extremely fast. This development is in the direction of the change of the propulsion system, and there is where we see that tire NVH is gaining more and more importance as well. The vehicle architecture is also changing, and this has impact on the behavior of the tire. The point is also that measuring the excitation coming from the tire is not that easy. It's actually a big challenge. And one of the way we can respond to this challenge is with our wheel force measurement product. They actually allow to measure not only the forces, but also the moments at the wheel axis. They ensure accuracy, repeatability, and consistency. Earlier in this webinar, I mentioned to you that consistency and repeatability are very important for TPA, because you want to make sure that actually the measurement you're taking today is going to look similar tomorrow, or it's going to be reliable if you do it on another object, on another, for example, in this case, on another tire. And so I think these products go in this direction. They make data analysis pretty simple because you can measure not only in time, but also in angle-based domain. So you can get both information, and the setup is rather easy. So you can just mount it on the vehicle or on the test rig or tire test rig, and there you go. The type of product classes that we have are wheel force transducers for on-vehicle testing, and then the wheel measuring apps for the tire test rig. And let's have a look at this second product line first, where we have the component, so the sensing component, which is it's mounted directly on the test rig. So you're basically mounting on the tire test rig where you have the drum. You see it here, and you can mount your tire attached to it. And the way it works is basically that you have your tire, and here is attached with the rim to the rotor. And then you have, of course, a stator, which belongs still to the sensor, where you have the piezoelectric sensors, for example, which are measuring the forces, and from which you're able to estimate forces in 3 directions and also moments. So you can take this information, and all comes with a rather compact shape. So this type of sensors are really compact. They are directly mounted on the test rig, and they offer a very high stiffness. We have also discussed about the relevance of having a stiff test rig to exploit at maximum the stiffness of the sensor. This is very important. So once you're mounting these sensors onto the test rig, of course, you have to make sure that you understand how the test rig is behaving, because this type of sensor really allow you to exploit a rather wide frequency range, definitely higher than the usual structure-borne range. And of course, the output that you're getting is in the non-rotating coordinate system. So you're not getting the information in the rotating coordinate system. Typical TPA applications are, of course, blocked force measurement, of course, blocked moment as well on the tire test stand. A good thing is that, as I mentioned, they offer a very high consistency and repeatability. So if you're changing tire, in this case, you can still rely on a measurement setup which is actually fixed, and you can master it. The frequency range is rather wide, rather broad, as I mentioned before, and they are available in various dimensions depending on the type of vehicle, tire, and application that you have at hand. And then we have a second class of products, which are wheel force transducers. These go mounted on the vehicle itself, so they are good for outside testing, for example, outdoor testing, and they basically measure the force which is traveling through the through the flange of the wheel force transducer. It goes through load cells, and then it gets measured. It gets quantified in terms of load outside. The design of this wheel force transducer is definitely modular and is optimized with CAE for the geometry as well as for the performance in terms of finite elements. They mount, depending on the version, 4 to 6 strain gauge, so high accuracy strain gauge load cells on the rim here, and they can measure up to 3 forces and 3 moments, which are calculated also in the non-rotating coordinate system. So you have them related to the axis, but not necessarily referring to the rotating coordinate system according to the wheel. And this is done in the onboard unit, which is called key road performance. The output can be both analog and digital, so you have both of them. They are very easy to operate and they are highly accurate because actually you can calibrate not only the individual cell, not only the whole system, but also the individual cells one by one. So this is a very high accuracy tool. And in terms of applications, of course, you could use them for direct wheel force measurement. So for example, if you want to measure for classic TPA the wheel force, you would get also in this case a rather consistent and repeatable measurement because the system stays as it is. You can change multiple parameters outside it, but the way it measures basically you can't change much, and it's available also in various dimensions depending on the type of vehicle that you have or the application. And here there is an overview of the products that we offer with respect to wheel force measurement. On the top, you see that we have the measuring hubs for tire test stand. Depending on the vehicle size, you have multiple of them, depending on the maximum load you want to apply to the sensor. You can choose, and then the signal that comes out of these sensors get conditioned by either the charge amplifier or, for example, the key road tire testing. These are very high-end signal conditioning, and actually I didn't go through it through this webinar, but of course part of our product lines are related to signal conditioning. So we have a wide variety of signal conditioners which allow you also to condition the charge which is coming out of a charge sensor, so a piezoelectric sensor. When it comes to wheel force transducers, we also have a wealth of products depending on the type of applications that you have at hand. As I mentioned before, with multiple high accuracy strain gauge load cells, and we also can offer the key road performance, which is onboard data transmission. So this hardware offers the possibility to acquire at 2 kilohertz with a cutoff filter at 500 hertz and up to 24 channels, which could be simultaneously acquired. At this point, I want to wrap up what we said today. So what we discussed today is the relevance of transfer path analysis for vehicle NVH engineering. So this is becoming more and more sort of standard. It's more and more relevant. But of course, a key message that I want to pass on to you is that accurate TPA requires the correct choice of measurement tools. So my suggestion is when you're planning your TPA, always keep in mind the way you want to measure, how you want to measure, and the various possibilities that you have, because they're going to deliver different levels of accuracy, and you always must take into account the most accurate way. We went through the broad range of solutions that Kistler offers, mainly for structural vibration within transfer path analysis. We had a look at accelerometers. Of course, we offer hammers and impedance heads as well for the excitation, for example, for FRF measurements. Force sensors, which would be standard force sensors, but also customized solutions for unique applications. We had a look at the wheel measuring hubs as well as wheel force transducers. Of course, we can offer a variety of accessories and cables, charge amplifiers and signal conditioning. And then there are some areas we didn't go through it, but Kistler also has products which could be useful in this direction, like strain gauge applications, torque measuring flanges, and in general also tools for measuring electric motor dynamics. And finally, powertrain analysis, where we have the new Keybox 2 together with in-cylinder pressure sensors, if you want, of course, to learn more about your engine when doing transfer path analysis. So I can only tell you and invite you that we look forward to get in touch with you, so to hear from you what are your applications to support the choice of the right sensor. And that being said, that I thank you for your time, I thank you for your attention, and I get the word back to Markus. Thanks.
So, thank you, Roberto, for your very important presentation. I would like to thank all participants for their attention, and I would inform you that we have recorded the session, and if you are interested, please contact us after it. And I wish you a successful time and look forward to your feedback. Please contact us. Thank you very much to all.